So welcome back. Today two pieces of electronics landed on my desk, more or less scrap pieces of electronics landed on my desk. That's an ATX power supply and that's a DLP projector that I bought on eBay. And also I found this Osram Powerstar HID lamp. It's as of yet unused, and the idea is to take components of these two products and mesh them together to get an electronic HID ballast. Because as it happens, this scrap DLP projector has an electronic ballast in it, and it's supposed to be, at least I hope it's supposed to be rated at the same wattage as this bulb is. And yeah, let's not check that first, otherwise I'll just stop it right here, because I bought this for another project and I found that the low voltage power supply was missing, and so the DSP and DLP chip and all the other ingredients are slightly less useful, because I'd have to figure out which voltages go to these 12 pins, and it's just frustrating. So yeah, there you have the light engine, and there's the DLP chip. It's the place where the bulb was. And there's your kaleidoscope, the color wheel, and a few other bits and pieces. But here on the side you can see there's an entire section dedicated to the electronic ballast. It also has the connections for the line-in, and it has the line-in filters and the capacitor. Maybe it also has a PFC stage. But yeah, let's tear this apart and investigate. So let's see. Just had to tidy up a little. So what do we got? There's this spring mechanism so that you can adjust the height. That's just ridiculous. Okay, have to push and then it's stuck. All right. Okay, there we go. Okay, there we go. See, it already comes apart. Okay, so that was easier than expected. Now for that high voltage clip. Yes, it's a nice high voltage connector. Unfortunately, the lamp is gone. It didn't come with the unit, and so I don't get the mating connector. Okay. So for the other side, I have to remove this cast magnesium part. But seeing as it's already broken, and I'm pretty confident that I won't be using the lamp. Let's get a few samples of magnesium, shall we? I wonder who does the castings, because they're quite nice. So there we go. This will leave us with a few small fans. It's actually a radial blower for a bit higher pressure that directly cools the lamp. And yeah, I might continue taking this apart just to figure out how they did the BLDC driver, because I want to work around the BLDC chip, or at least the BLDC channel. I wonder if I can see this. Maybe I'm out of frame. That flat flex cable, it's a 4-pin cable, goes directly to the BLDC motor, and up on the BLDC motor you get an optical encoder. Well, that's just a tachometer, and it's connected to the main PCB. And on the main PCB you got the DSP controller and auxiliary controllers, and you have to synchronize the DLP chip control data stream to the periods where the color wheel changes color. you can see, no, sorry, you can't see it. Maybe there. Yeah, there you go. Those are dichroic filters, so they reflect the complementary color to what is being transmitted. So the yellowish tint originates from the blue filter, and the turquoise tint is associated with the red filter, and the pinkish tint is for the green filter. And there's a clear segment for the white. That's just anti-reflection coated. And somewhere on there, or maybe on the motor. Oh, there you go. You can see this piece of black tape. At least I hope you can see it. There's the black tape. So that would be an optical encoder. Let's check this out first, and then we'll go. Wait, let me pause. Let's undo this. I wonder whether the word scrutiny has something to do with unscrewing screws. So, oops. There we go. Yeah, that's a reflective optical encoder. Maybe you can see the two bumps. There's the transmitter and the receiver. That would be an infrared LED and a phototransistor. And they are also connected to the main board. So, yeah, labeling's not that conclusive. So at least this generates a sort of signal. Okay, put it back on, just for later entertainment. And let's get back to the HID ballast supply. Maybe even we can trick it into working with a different power range, power setting. Okay, here's your output, and those are both high voltage leads. So the ignition transformer, that's the point that you have to look at every unit that you take apart. This is a unit for a lamp with two wires. They're both high voltage wires. And that would be a unit where there's a coaxial or inline high voltage ignition transformer. But there also exist lamps with a separate ignition electrode. Wait a second. As with these xenon flash tubes. This is a larger 300 watt second xenon flash tube, and you have two electrodes and one wire wrapped around it, just to ionize the gas inside and get the arc to strike across. But this is for pulsed operation, whereas the high intensity discharge lamps are for continuous operation. And they also have a very complex startup sequence where you have to start with a certain overcurrent to heat the lamp up, and as the lamp heats up and the pressure inside increases, the voltage across the tube also increases, and you have to limit or at least track the power and constrain it within a certain range. And as the lamp ages, the operating pressure also changes, and you're not always able to keep the lamp operating. So you lose the lamp as it leaves the operating window. Maybe the pressure is the required pressure for normal operation. I gotta try the other way around. The operating voltage gets higher and higher as the pressure changes, and some lamps will start cycling as they age, and some lamps will burst. There's also a change in the material, so that the glass, so the unordered glass structure starts to recrystallize under higher temperatures, and then the glass envelope gets partially crystalline and more prone to fracturing. And that's also a mode that occurs after several thousand hours of operation that makes high pressure and highest pressure lamps prone to failure, and that's one of the possible failure mechanisms. So again, another piece of magnesium. Maybe light a piece of that with a torch later on. So yeah, screws, 2 screws. No, I just see 2 screws on board. Let's take these out without damaging anything, and then we go into the details on what we are seeing on the PCB and what the functions of the different components are. because I want to understand the module and use it for our purposes. And the first thing that you can see is this small side PCB. This will be, and it also has a 3-pin connector. This will be the main interesting part. And come on, let go. And that's more or less the control interface. You can see 2 optocouplers there, and usually one is the enable signal or the interlock signal, and the other one is the power good signal that is returned from the board. And some variants may also transmit the sensed current or operating state via the return optocoupler, or they have a second optocoupler. Just let me look up the numbers and I can tell you a bit about the optocouplers I used. So I just looked those 2 parts up. One is an SFH 6156-3. That's your generic infrared or gallium arsenide infrared diode emitter. And phototransistor optocoupler, that's a very simple device with a 4-pin DIP package. And the H11L1 is a bit more sophisticated. As I mentioned before, they come in different styles and speed grades. And this one actually goes down up to 4 microsecond pulses, and it has a logic gate with a Schmidt trigger on the output. So that makes it a bit more comfortable to work with when you attach microcontroller, because then you don't have analog levels that you have to latch, and you don't get this states in between that you have to interpret. So yeah, that's the convenient choice. This one is from the power supply. Let me just check. Yeah, this is from the HID ballast to the main control board, and the other one is for the return direction. So that's a bit surprising. Maybe they just thought, well, we use the logic level for the small onboard controller that you have there, so just to make it a bit more convenient. There's another one that's the same guy. Yeah, that's the same, and it yeah, we'll see what it does. At least perhaps we have to. So okay, the fuse is missing, and there's a connector that I'll go into detail right away. Just yeah, let me just get the board out and then we'll see what it does. Okay, so when you want to make these work, you have to supply. You may have to supply a voltage to this optocoupler. No, wait, it's the other way around. To this one, to the 6-pin device, and then it will activate the power supply and start the power-up sequence. So it will turn on the ignition, wait for a certain time interval, see whether the tube strikes or whether it doesn't. And if it doesn't, it goes into fault mode, and the power good signal will turn off again, or at least it won't turn on. That's different between whatever model you get. So now you only have, there's a clip, a plastic clip, and then the 2 screws, and then we should be good. Just like this. And there we are. Just get out that. There's more magnesium casting. That's just ridiculous. So there's isolating sheet. Oh, look nice. It's also made from Osram. Made by Osram. There are huge SMC package rectifier diodes, and yeah, there's the controller print, and there's the power section. It's mostly the power section. So let's see what we got, and then I'll look up the model number and see what the power rating for the bulb is, and that will decide whether we can use this at all, or maybe we can mod it. There's a trim port for something, or maybe we can change some resistors. Oh, it has the power rating written on it. It's 120 watts. Osterried. Oh well, maybe that's just the model. 120 W/5. Let me check. Now, what do you know? The lamp it draws 185 watts total nominal, and 120 watt is for the lamp. So yeah, we are a bit underrated for this lamp, but we may get it to strike, and we'll have to live with reduced light output. We'll see. Maybe it will not reach the temperature that it's supposed to reach, and yeah, at least we can try. So yeah, okay, where was I? Wanted to investigate the type of controller. There's an L6561D. Is that correct? See, there are components on both sides, and the bottom side has all the assembly components. And now we can check out what exactly we're seeing here. So I expect some driver circuitry for this power devices. Those are TO220, or the variant that has the isolated tab. And this just look like filters, and I'm missing the power magnetics. This may be the switch mode transformer or switch mode inductor, because it has a multi-fella winding, and it uses fine wire, so that would be used for high switching frequencies. It also has a small wire wrapped around the outside of the winding that may be for shielding purposes. And there's this huge low dissipation 1.5 microfarad polymer capacitor, and power just the main capacitor, main electrolytic. This looks very much like the DC-DC converter cell, or at least the driver cell. Okay, and there are the power MOSFETs. Yeah, looks like an H-bridge configuration. So yeah, we might actually be running this with a buck converter, or directly from the PFC intermediate circuit, and use an H-bridge to drive the lamp. So you don't get a DC current through the lamp. You just alternate and change the polarity, so you don't get mercury migration inside of the lamp and uneven heating. So the lamp design is mostly symmetrical. Let me get this one out. There are two tiny, really tiny electrodes, and there are tungsten tips. I'm sorry, you can't. The camera won't focus, and I lost my lens. So there are two very tiny pointed needle electrodes that are inside the inner glass envelope, and that might actually be an alumina envelope with zirconium dioxide or zirconium oxide on the outside, so as to reflect the infrared radiation and keep the inside hot. And this one also has UV filtering glass, which not every tube, every bulb has. Okay, so those are the power fades, and now let me give me a moment, and I'll look up the part numbers of at least this controller, or whatever it is. Maybe gate driver, maybe something else, but yeah, it's ST, an ST part, and we'll see what it does. It's 6561D. And as I'm always struggling to do things in the most ghetto way possible, here's the data sheet. It's an L6561 from ST power factor corrector, so that would be a PFC controller IC, and it comes with the D variant in an SO8 package, as to be expected. And here's a block diagram from the part. Maybe just briefly go into. There are a few ways to implement a PFC controller. You may, for example, use discontinuous conduction mode, and just as the the sine wave evolves, you can just do current spikes to track the voltage curve. So that's your current over time, and that's your voltage over time. And when they track, you usually get a good power factor. Usually, when you have discontinuous conduction mode, you have to do a lot of filtering, and as you go into continuous conduction mode, the control scheme gets slightly more difficult to implement. So what we got here, we got a zero crossing detector, we got a starter. I got enough time. There's a voltage regulator or voltage detection, and usually you have to have a multiplier. So you take your feedback, and you scale the amount of current that you have to draw with the difference between your nominal intermediate voltage and the current intermediate voltage. And everything is multiplied by this envelope of the voltage function. So that's good. And as an output, you just have this hacked together driver, and you have to figure out a way how to supply 12 volts or something like that to get proper startup. And there's a Zener diode for a 20 volt clipping. So you may have a resistor that trickles some charge in, and a capacitive power supply that gets the startup done, and then you have an auxiliary winding on the PFC choke to generate the operating current. And usually in a good design, you'll deactivate the trickle resistor so as to remove this heat source and source of unnecessary dissipation. And sometimes I wonder whether they just use the reference design and then come up with the particular ratings. So maybe often you find on PCBs a design that is very close to the reference design in the datasheet. But datasheet reference designs also have their shortcomings. Maybe they're just a bit rough, maybe they just leave out the essential parts for filtering, for ringing suppression on the rectifier diodes, or the nasty little catches that you turn up when you investigate a circuit and try to improve it. So that's what I promised. You have an auxiliary winding on the PFC choke. The intermediate voltage is set at 400 volts. We'll have to see whether that coincides with the PCB that we have, or whether it's something else that would just result in changing these resistors. Those are multiple resistors in a chain. So maybe there's a footnote that explains that you have to do that to distribute the voltage drop across several 1206 SMD resistors. And there's an AC sensing going on here. There you have the gate driver, you have current sensing with pin 4. There's a 0.41 ohm 1 watt resistor. So that's where the VCC is being generated on pin 8. You have maybe the pin 5 is also used for current sensing through the inductor, and there you have what looks to be a charge pump. You have this RC series network, and there's the Schottky diode, a normal silicon diode, and this acts as a charge pump, and it just supplies some current to C2 and to the VCC rail, and that is used for the gate driver and the control circuitry. And just another word on the operation mode. They say the device is operating in transition mode, and it's optimized for electronic lamp ballast application, AC-DC adapters, and switch mode power supply designs. And what they're basically saying is this is using boundary conduction mode, where you get the best peak density, or at least the best pulse density and highest operating frequency, hence smaller components, while still maintaining this zero crossing. And this is a great advantage because it reduces the losses during switching, especially when you turn on the device. You're turning out with zero current. And this is discontinuous conduction mode, this is boundary conduction mode, and this is continuous conduction mode. And as you can see, you have to switch off and on hard. So hard switching means that you don't get zero current switching or zero voltage switching. And this is an optimized way to reduce dissipation. And just because I'm getting a kick out of it, there's the FAN 9600 series dual phase interleaved boundary conduction mode PFC controller. And that's a very fun chip. It has a power path with 2 MOSFETs, 2 inductors, and a double diode. And as I mentioned, these spikes, they tend to cause lots of interference, and you have to apply serious filtering. And as with multi-phase DC-DC converters, you can reduce ripple current and dissipate and need for filtering by just adding multiple phases and overlapping them. In this case, 180 degrees out of phase. The inclined reader can check this out in the just too much. Can check this out in the manual. They also give you an example circuit where you see everything is implemented twice. You have 2 current sense resistors, 2 fades, 2 diodes, 2 power inductors with auxiliary windings, and they are most likely used for current sensing. So yeah, what I wanted to show you here is maybe some waveforms. Would be very nice to have them. Okay, so no waveforms here. Oh, there we go. Yeah, that's what we're looking for. Okay, so that's the main diagram. That's mostly everything you need to know. You can see this these 2 half cycles of the line voltage, and you see the inductor currents for IL1 and IL2, and the sum of them, that's the current that is drawn from the filter capacitor. That almost approximates a sine, the absolute value of a sine wave, and you have this residual noise on the waveform. So you can see the overall amplitude is reduced when compared to the single phase, and this is the combined current for the 2 channels. So usually you'd have to multiply the single phase waveform by 2 to get the equivalent current power transferred. So that's a significant reduction, and you get filter inductors that are almost an order of magnitude smaller than they would be with a single phase converter. And it saddens me to see that in the ATX power supply that we'll maybe investigate later, that they just doubled this single phase power path, basically increasing the noise by a factor of 2 and going beyond the limits of the component. And Osram being Osram, they have not skimped on the PCB at all, which makes it slightly more difficult to reverse engineer. Maybe you can see the darker areas underneath, and they're underneath the surface layer here, and they're underneath the surface layer here. So that's, I assume it's a 4-layer PCB, where there's an inner ground plane, as you'd expect for a high-quality DC-DC converter. So you minimize radiated power, and maybe there's also an inner signal plane. And you can see that the inner plane is connected to this heatsink metal piece, so that's a strong indication for it being just a ground plane or a shield plane. And it also has, even in its inside, and it's laminated with epoxy, it has a large clearance of almost 100 mil or 80 mil towards any signal or any DC path that's inside. And there are small, very funny details that you can pick up when you look at the PCB. Maybe you can see this reflective sheet there. That's just like a overhead projector foil, and that is underneath the main capacitor, or this series capacitor, to improve electrical isolation. There's a small track running to one of the pins of the header, and even though there are 4 pins, only every second pin is actually connected. And I can then, actually I can show you what's going on inside the PCB. There you can, maybe you can just barely make out this single trace that comes over from the left and goes to the rightmost pin of the header. So that would be our ground, and the other trace just goes to the rectifier. And yeah, given the position of this rectifier diodes, those are, no idea, T549M, whatever. I suppose they're line voltage rectifier diodes. They don't need to be fast, they just need to be there. They're put in there, I suppose, after the line filtering or in between the line filter segments. So you use the inductance of the common mode chokes to reduce the recovery current. It just slow down the recovery for the diodes, so to minimize RF interference and dissipation in the diodes. And yeah, with only one trace left, I'm pretty confident that this is just the PFC stage or input stage output for the missing power supply that supplies the 12-volt rails. And that's a good sign, because then this module is self-contained, and that's not with the other one where we had to supply 12 volts via an additional power supply. This also supplies the power for the controller via some auxiliary winding on the PFC chokes. So yeah, and that only leaves us with the funny lamp control section and the igniter circuit. And this is an EBCOS spark gap over the output, so when no lamp is connected or when an over voltage condition occurs, you don't fry the transformer or get internal arcing, and you also don't flash over on the tube side. So one thing left, whack in a fuse, see if it runs, and see if we get a lamp ignited. Yeah, pollen fuses. Ein Püschelprodukt, kompromisslos sicher. That's very German. That's your 2 amp 250 volt slow blow fuse. And the reason I'm using this 2 amp fuse instead of a 2.5 amp fuse is because 2 instead of 2.5 is pretty much okay. They don't have a rating for the, oh, that says T. Okay, so that may be träge, so that's slow blow. And yeah, you won't be operating this with 120 or 110 volts, so we should be okay, right? Should be good. Now we can power it up, and then we just measure the intermediate circuit voltage and see if the PFC stage is all good and working. But given that this is a very nice Osram module, I don't expect it to be messed up in some way. They also use quality caps, so no issue with that. First of all, the flame test. Now, let me plug this in and see if the fuse blows or anything lights up. Oh, that's a good sign. So, can you read the multimeter? So, let me see, let's not touch anything. There you go, 330. That's a bit lazy. That's just rectified mains. Okay, so they're not going for the 400, they're just going for 330. So, one possible cause may be